Hello viewers, I am Kausalya. Today we are going to solve problem number 10 in time response analysis. And the problem is a closed loop servo is represented by the differential equation. Okay, this is a differential equation. Here we are having some terms as C and E. So here E is nothing but E is equal to R minus C, and C is the displacement of the output shaft, whereas R is the displacement of the input shaft. Right, this is a servo system which obeys this characteristic equation, and this characteristic equation has some constant terms, that is C and E. For each that is for C and E, they had given explanation what is that, right? Here E is nothing but R minus C, and R is nothing but displacement of the input shaft, and C is nothing but displacement of the output shaft. And here E is the difference between those two shafts, right? The next thing is find undamped natural frequency, damping ratio, percentage maximum overshoot for unit step input. Finally, we are asked to find the undamped natural frequency, that is omega n, damping ratio, that is zeta, and maximum overshoot value for unit step input, right? So here the differential equation is given, and our first step is we have to form a equation in the form of C of S by R of S, right? So that it is easy for us to find the undamped natural frequency, a damping ratio, and this overshoot. So the first step is here, this is our given equation, t square c by dt square plus 8 into dc by dt, which is equal to 64e. Right, and here the value of E is given as R minus C, so just substitute R minus C in the place of E here, right? And our first step is we are going to take Laplace transformation. So when you apply Laplace transformation to this equation, what it becomes, that is d square c by dt square will get modified as s square into C of S plus this 8, here the same 8, dc by dt, when you take Laplace transform, we can write it as s into C of S, so which is equal to again 64 into R of S minus C of S. Okay, these are all the basic things we have studied in our chapter 1. And the next thing, just we are going to arrange C of S terms together. So here s square into C of S plus 8s into C of S, and here we are having 64 into minus C of S. So when I bring this minus C of S into 64 to the left hand side, this minus sign becomes plus here. So plus 64 into C of S, which is equal to 64 into R of S here. So here in this term, we are taking C of S commonly outside. So the remaining terms will be s square plus 8s plus 64, which is equal to 64 into R of S. Right. Now, what is our ultimate aim? We have to find the ratio of C of S by R of S. So just arrange accordingly. You bring this R of S to the left hand side. So the remaining terms will be this 64. And here this term in multiplication, when we move to this side, becomes denominator. So 64 divided by s square plus 8s plus 64. This is our C of S by R of S equation. So from this equation, we can easily find the damping ratio, peak overshoot, etc. etc. So here now I am going to compare this equation with the standard format of another equation. So what is the standard format? Omega n square by s square plus 2 zeta omega ns plus omega n square. Now we are going to compare these two terms. On comparing, here in the place of omega n square we are having 64. So omega n square equal to 64, and finally omega n is nothing but 8 radians per second. That is square root of 64 is 8. And the next thing, comparing coefficient of s. So 2 zeta omega n is equal to 8 here. So just substitute the values here. Here we know the value of omega n. So zeta is equal to 8 by this 2 into omega n occupies the denominator part. In the next step, just substitute the value of omega n. Here 8 and 8 cancel each other, and finally the value of zeta is equal to 0.5 here. And the next thing we need to find is maximum overshoot. So what is the formula? Percentage maximum overshoot is given by e power minus zeta pi by root of 1 minus zeta square. So here we know the value of zeta as 0.5. So just substitute the values here, and finally we are getting the answer as 16.3 percentage. Right? That's all. The problem gets over here. Hope you people understand well. Thank you.